track. So he got his PhD. So his PhD in San Diego. He got the postdoc in Santa Barbara, and now he's a faculty in Nebraska University. So he will talk today about the multilepton analysis in CMS and plans for the future. So,
thank you. Thanks for inviting me to be here. This is second trip to College Station, and since I came somewhere from, it was quite a bit colder than here. It was nice to wake up this morning and walk out into a nice spring day. So right, as Lucas said, I'm going to talk a bit today about some of the work I've been involved in with colleagues recently on CMS. And, okay, so title started off with Multilepton, but we'll see if it stays there. So we're living in an age of exploration, I would argue, though. This has been a fairly unique time for collider physics, in that we've gone through this period of successive rapid increases in both the energy and the luminosity. The most recent, a couple of years ago, when we moved from 8 TeV to 13 TeV. On the left here, you can see shows the ratio of parts-on luminosity. So it's a rough gauge for a given center of mass energy and production mode, roughly how much gain we expect in cross-section from the increase in energy. And so the combination of this happening several times, first from the Tevatron to 7 TeV and then again, and as well as the rapidly accumulating data sets that you can see here, has allowed us to really pursue searches for new physics very aggressively. And the question really is, this has been a great area of exploration, but will it end up being an area of discovery? And that, I think, remains to be seen. But kind of, you can start by writing down what are the guidelines to sort of tell you where you should go as you begin this exploration. And there really are two generic categories of searches and measurements that we can look at. I mean, the obvious place is look for something that's spectacularly new. A new resonance you haven't seen before. Okay, we did this and it actually worked pretty well, right? We found the Higgs boson a few years ago, and then before that, resonances have a long history of great place to discover something new. Or to look in tails of distributions, look for, huge excess of events with lots of energy, perhaps lots of missing energy and balance in the event, large number of leptons. There's various ways you can go about this, and almost all of them have been tried in one form or another, the LHC. Another option is to try to do precision measurements. If the first doesn't work, instead let's look for something that's really rare. Frequently it's in a region that has large backgrounds because its kinematics tend to be close to the bulk of standard model processes. And in contrast to the above, which is really about understanding, estimating backgrounds and tails of distributions, and not being so sensitive to the uncertainties on those backgrounds, these precision measurements are all about understanding the backgrounds in detail. They're typically systematics limited, not statistics limited. So we're trading off sort of challenges to the different approaches. And because of the series of increases in energy and luminosity that we've had so far, most of the searches have really all fallen in here in one way or another. There's been very little in the way of aggressively looking for new physics through the second route, and that's okay, because start with the low-hanging fruit, and this strategy has worked really well so far. I show here, I just picked one of the results I've worked on in the past. It's a search for new physics in jets plus MET, and it's showing you sort of the analysis strategy from 2010 to today, and the results that go along with it. And basically, as we've increased the energy and luminosity, we just keep looking further and further in the tails. Here you can see this HT is sum of jet energy. It's a measure of kind of the total amount of energy in the event. We started off at about 1,000. We've increased it to 1,500, and correspondingly, we've asked for more jets, more missing energy, and we just kept pushing further and further to the right. And what we've been able to do with that is we've been able to probe increasing areas of parameter space. And when the LHC started, we were kind of talking about neutrinos that were 500 GeV or 1,000 GeV. Now we broadly exclude almost everything at a TeV, and many things all the way out to a couple of TeV. So it's been a successful and rapid push to probe higher masses. Unfortunately, it hasn't turned anything up. And it isn't just jets plus MET this has been done, and this has really been the strategy for most of the program of new physics searches. I'm showing here just the an unreadable summary of all of the results for searches, what we call SUSY, but it just means searches with large missing transverse energy. And when we started, kind of all of these lines were somewhere down here, and they've been pushed far to the right, as you see. Unfortunately, you could say that the future isn't what it used to be, as Yogi Berra would say. If we just take the exact same approach and we try to replicate it for the next few years with no increase in energy and relatively much more moderate gains in luminosity, the gains are going to come a lot slower. Remember, we started over here at the start of the LHC and we managed to push it to here. With the next, this is through the end of 2016, this data in blue, and if we add 3 times more data by the end of this year, not moving very far. It's hard to get excited about this, isn't it? So I think that, we could keep going this way. I mean, there's some options. One is be patient, just sit around and wait for much larger data sets, and eventually this will creep further and further to the right. If you look at the long-term projections, we're supposed to be able to exclude up to about 3,000, so we still have a ways to go. But it's also going to be about 2035 before we get there, which is a long time to wait. Another option is understand the backgrounds a lot better. Maybe you can reduce your systematics by a lot, and then you can keep doing the same thing, but be sensitive to physics that you weren't before. And of course, the other option is just kind of toss this one to the side and come up with a new approach. And so this is kind of the questions a lot of us have been asking ourselves as we are changing the pace of things at the LHC from this era of rapid increases to one of much more gradual increases in the size of the data set. So, well, for the first one, I'm not patient enough to wait 15 years to find new things. So that one doesn't work. And the second, honestly, gives me a lot of indigestion. I'm really not thrilled about the idea of convincing myself or anyone else that we really understand these things at the percent level or whatever it is that you say you need to do in order to make the precision measurement route work. But at the same time, I still think the LHC is largely a discovery machine. I mean, I want to look for something new. I don't want to. There's important things to learn by measuring, sort of very classic inclusive standard model processes like W and Z production. But unless we do it in a certain way, we're unlikely, I think, to really gain insight into potential new physics that could be hiding there. However, I'm also bored with just setting limits. So I don't want to do that, and I want to just keep making the plots on the previous slide. So what can we do? Ideally, I'd like to pursue some physics that lets me measure something. Be a change from what I've been mostly involved in the last few years. But I want to measure something that also is sensitive to new physics and lets me do it in a way that I don't need to understand my backgrounds at percent or even 10%-ish level in order to be able to potentially find something interesting. And I'd like to ideally find an approach that can remain interesting throughout the next several years as we begin this process of more slowly accumulating data. And so today I'm going to try to sell you a bridge, I guess is the saying goes. I'm going to argue that we should study events that have either a pair of leptons with the same electric charge or 3 or more leptons. And so after I got to this point, I realized that this wasn't actually the talk that I wanted to give exactly, so I'm going to go ahead and change the talk on you a few slides in. Instead of multi-leptons as the winner of the standalone, I'm going to argue that we should look for 4 top quarks. And the best way to do this is with multi-leptons. Okay. So you may be asking, why 4 top quarks? In fact, haven't you already been doing that? It's kind of what I showed you in some of the success of JETS plus MET earlier. Here's an example SUSY search for partners with the gluino, and each decays to, in this case, 2 top quarks and some non-interacting particle. And we've had a lot of success pushing out the constraints on this. Up around 2 TeV, you can see it's done in many final states, including same-sided multi-leptons, which you may be looking at this and notice, why is everything over here and then the same-sided multi-leptons are hiding way down here, barely contributing anything? And it's because almost all of these searches are not getting their power from anything to do with this here. They're getting it from this. It's all MET. It's asking for a large MET. And once you have that, the other stuff, helps, but it's not the primary thing that's giving you sensitivity. So you could ask yourself, what if there was an additional MET? What if I produced this, but this wasn't here? Is that an interesting signature to look for? And why should we go looking there? And so, try to make a bit of a case for why I think 4 tops with no ret may be an interesting place to look. The first is because it's there. The standard model says this gets produced, mostly just QCD process. There's no real reason to expect, first, nobody probably doubts that this exists, right? It's just the physics we know. And second, we probably even can calculate the rate correctly. It's sometimes done, right? Because this is physics that we understand. On the other hand, when you start looking through the literature on it, you get numbers that are all over the place. 3 recent papers, you have this one that provides a 14 TeV calculation at NLO. Get something like 15 femtobarns, but that can change by about 20% depending on the scale that you choose. And you get this paper from the MadGraph authors. They calculated at NLO with MadGraph. They get 9. So this is 13. The 13 to 14 isn't expected to explain all of the difference, but it accounts for some of it. Then you have this other paper by Chow et al. They only provide a leading order calculation, and their leading order number is bigger than the NLO number from the MadGraph paper, even though all sources claim K factor is greater than 1. So there's some uncertainty here as to what the real number is. And so you can try to go ahead and measure it just for the sake of, we should tie this down and help clarify this. Although I think, proper theoretical treatment and sorting out, understanding all the differences here is likely to give us a number that agrees with what we have. So that alone I don't think is sufficient reason to want to go look for this. But another thing you may have noticed in the previous slide is that this cross-section includes diagrams that have a Higgs boson. And while this contribution is expected to be relatively small, you can see at leading order the contribution is broken up at different energies. So at 13, we get about 10 femtobarns from just the QCD molecular weak part. We actually reduce this some due to interference between the Higgs diagram with Higgs and the diagram without. So you can see that interference term is -1.5. This diagram alone contributes about that much. But it's interesting because it comes in with 4 powers of the top Yukawa in cross-section. So we're very sensitive to the top Yukawa coupling in measuring this cross-section. And here you see, based on these numbers, what the cross-section is for producing 4 top quarks for a different choice of the top Yukawa. Because it goes like the 4th power, for a top Yukawa that's a factor of 2, we get a doubling of the cross-section. If it's a factor of 2.5, it's almost a factor of 5 increase in cross-section. So if there were some physics that could modify this coupling, we could potentially see it relatively quickly by looking at 4 top fun states. Of course, that's not the only reason I think that 4 top quarks are interesting. If we move away from the standard model a little bit towards more speculative scenarios that are of interest, that are interested at least a lot in the collider searches today, one is scenarios with 2 X-delta models. It's interesting because it's realized in a lot of new physics scenarios, including supersymmetry. It provides a fairly rich phenomenology. We get two scalars and a pseudoscalar plus 2 charge phases. And it turns out that there's some interesting regions of unexplored parameter space here to go after. In particular, if we go to this region called the alignment limit, which is attractive because it will result in the lightest scalar having properties that are consistent with what we would expect for the standard model dates. It will also suppress the VV couplings for both the heavy scalar and the heavy pseudoscalar. And if we go to low tan beta regions where the VV couplings are suppressed relative to the TT bar, then this is a region where there's relatively little that colliders have been able to say up to now about the existence of heavier Higgs bosons. You can try to go at this most directly by direct sort of gluon fusion production. It certainly has the largest cross-section, but it turns out it's a challenging way to go about this because there's a very large background from and interference with QCD TT bar production. You can see down here this is for a scalar 500 GeV and 10 beta 0.4. You see this blue histogram is what the signal looks like. The red is what you get if you generate it with including interference between this process and then the QCD one. And what you see is that the line shape gets distorted a lot. And also, that this depends greatly on the value of tan beta. If we go from tan beta of 0.4 to 2, it becomes much, much narrower. And this thick and deep structure all takes place within a window that's smaller than the typical experimental resolution we have on the TT bar resonance. So it becomes very difficult to try to pick this out. Okay, but that doesn't mean it hasn't been tried. Both Atlas and CMS have done it. Here's some results from Atlas, and you can see with, so this is with the end of run 1. They probe a little bit of this corner. And you should read this as they really only probe the region enclosed here. If you go to lower masses, then you quickly fall off and can't say anything because of the interference that happens here. However, people saw this, and it was pointed out by Nathaniel Craig and collaborators and some other papers as well, that you could try to probe this by looking for associated production. Instead of looking for gluon fusion, look for TT bar Higgs production, or TT bar pseudoscalar production, and have those decay to TT bars, so you get 4 top quarks in the final state. And this can happen via a few different production modes. There's the TT associated. Here, there's also sort of the analog of our TW production, as well as a single top production with just a light flavor quark. So we get all of these. You can see kind of what the expected cross sections are here for the individual processes. This is assuming 10 beta 1, how they compare to the standard model 4 top. So you can see that you get a large enhancement for low values of a scalar or pseudoscalar. On the right here, just showing the total cross sections for both the scalar and pseudoscalar. The pseudoscalar tends to be a little bit larger cross section. We can overlay the same equivalent processes, triple top plus W and triple top plus Q for the standard model, and you see it's a negligible increase compared to what we would expect if there really was heavy scalars or pseudoscalars decaying this way. So this is another reason for top fusing. It turns out you can probe some interesting regions of 2 Higgs doublet models in a fairly general way. And so I'm going to argue that those 3 things are sufficient motivations, but I want to go look for this. Measure something that hasn't been observed before. Potentially probe deviations of the top-U-power coupling, and look for extra Higgs bosons. All right, so how would you go about searching for 4 top quarks? Well, there's a variety of final states that you can give. The relative branching ratios for all of them are showing in the pie chart down here. There's all hadronic, which is about 40% of the total, but it's just completely swamped by TCE background. And so it's not explored at all here. Although it turns out is an interesting aside maybe, that there are searches for RPV SUSY, looking at all hadronic and 1 lepton final states, that we're able to get some success by essentially looking at the sum of jet masses, so clustering large radius jets. Processes with a large jet multiplicity will have higher accidental overlaps than processes that don't, your backgrounds. And so by looking at the sum of large radius jet masses, it turns out they've been able to get sensitivity to RPV scenarios, and they've attempted to apply it here. But right now it looks like it's going to be a long way to get there, but it may not be completely hopeless. So people are working on all hadronic searches in this channel, but I think it's going to be a while before we see anything from them. But there's much easier ways to go about looking for it. With the same branching ratio, we can get at least 1 lepton. We get about 10% of events with opposite sign dileptons, half that amount with same sign dileptons, and a few percent of multi-lepton events. And so the LHC so far, the results have all been with at least 1 lepton. You can see some results from very early on in run 2 data taking here in the upper right. The expected limits, this was all in terms of limits on notice on views. So this is a limit of 26 here, means 26 times the standard model cross section. This was very early with no sensitivity. But it gives you a flavor for the relative importance of the various searches in terms of of what they can be expected to contribute. And what you'll notice is that the same sign dilepton here is quite a bit more sensitive than either the single lepton or opposite sign dilepton, and it drove most of the early combination. And the reason for that is even though the fraction ratio is small, it's only about 6%, you lose half the signal compared to opposite sign dileptons, but you get a massive rejection of your main background. The main background is TT bar plus jets. You'll notice the leptons, of course, that you get if the W's decay their opposite sign. So how do you get a same sign lepton pair in TT bar events? Well, you need one of the W's to decay leptonically, and you need the B from the other top to give you a semi-leptonic decay, and you don't identify it as being a jet. Maybe it fragmented primarily to a leading lepton with not a lot of stuff in the isolation cone, and it looks like an isolated lepton, even though it really isn't. But this requirement turns out to provide several orders of magnitude reduction of the TT bar background and gives us a fighting chance to really go after this signal. And in some ways, you can think of in the tails of standard model distributions, but in different types of tails than we've been looking at up to now. Okay, so I'm just going to have one slide on the 1L and opposite sign 2L. As I mentioned, the TT bar background is very large, so it requires a very aggressive approach. So analyses each use two multivariate techniques. One, training a VDT on TT bar Monte Carlo just to try to reconstruct hadronic top decays. Train kind of a fairly standard list of variables. Masses formed from combinations of jets and angular variables between the jets. And then the output of that VDT is fed in with a whole bunch of other kinematic variables to a second VDT, which is then used to try to discriminate pore top production from TT bar production. They classify by N jets and NV and bin up the VDT output. And in the end, they get order 100 signal regions or more. You see all of these bins here. You see most of them, the signal's just hopelessly lost underneath the background. And this is signal scaled up by 20 rate. So it's really a difficult thing to go after. And depending on your taste, you could argue, okay, you've chopped it up in all this way, but it turns out you get a lot of constraints on your backgrounds from over here. And you can ask yourself, how much do those backgrounds have to do with the backgrounds that are living over here where you're actually trying to extract your signal? Okay, this was a very early result. Those updated results were just internally approved, so they should be publicly, sometime this spring, you should have updated results in these two channels of the 2016 data. But what I really want to talk to you about today, since I said multi-leptons at the beginning, is looking for this with same sign dileptons and multi-leptons. And what is the strategy to doing that? So this is based on the full 2016 data set and came out on the archive at the end of last year and was just accepted for publication a couple of weeks ago. So we start by selecting events with either same sign lepton pair or at least 3 leptons, and we count the number of jets and VTEGs. As I mentioned before, TTOL with opposite side is heavily suppressed compared to the 1 lepton and 2 lepton. And you can see here what an example looks like for 4 top production. If I ask the 2 top quarks decay leptonically and the 2 antitops decay hadronically, in this case, I get a same sign lepton pair. And at least at generator level counting partons, I get 8 of them, 4 of them which are Bs. That's a pretty spectacular signature to look for. We can ask for more leptons, but each of those comes at the cost of losing 2 jets. Although we still keep our 4B jets potentially, and so we still have some very powerful handles to try to go after this. And what we opted for was a much simpler approach. You can see we have about order 10 signal regions in total. They basically chop it up by a number of leptons because the background composition depends on them, as well as the number of jets that are VTAG and the total number of jets that we have. We define a couple of control regions to isolate 2 of the main backgrounds that I'll talk a bit more about later, but these are a region to go after TT bar W production and a region to go after TT bar Z production, which are called CRW and CRZ. So just to show you a little bit what the signal kinematics look like, and why number of jets and VTAG jets is a good discriminator, you can see here unblinded distributions of all of the, blinded distributions with all of the estimated backgrounds and the signal overlay for N jets and NB, and you'll notice that the Interestingly, even though we had 8 jets, the n-jets distribution, even for signal, peaks around 6. Turns out that we lose jets at a higher rate than we like. Some of them are from acceptance. You get a jet that goes too far forward in the detector or is too soft, too low PT. You don't count it. You also get, which I had mentioned earlier about this large radius and jet masses, you get overlaps. It turns out you lose about a jet per event on average because 2 of the partons often end up pretty close to one another, just because there's 12 of them. You know, there's 8 of them or 10 of them, or however many things are flying around in your event. It's easy for 2 of them to wind up close to one another. The B tagging peaks around 3 for signal, only 2 for background. And here the reason it's 3 and not 4 is just our tagging efficiency is finite. It's about 70% tagging efficiency for the B tagger that we're using here. But you can see you get decent, as things go, you get not such bad separation by using n-jets and NB between the 4 top and the standard model processes. So what are the backgrounds that populate that? There are a lot of colors there. Turns out there's 3 main sets of processes. One is processes that actually don't have a same sign lepton pair or 3 leptons, but instead have a fake lepton. Or I'll use the word fake a lot today, and what I mean by fake is a jet misidentified as a lepton. This mostly happens in TT bar events, and here typically it's a B core, semi-leptonic B decay that we identify as a lepton. Or it can be unidentified conversions. 2 likely ways we get fake leptons. We can also get processes with charge mismeasurement. So we get a lot of opposite sign dilepton TT bar events. And every once in a while we mismeasure the charge of one of the electrons in the event, and it becomes a same sign event. This mostly comes into our analysis via TT bar events as well. These are both estimated from data-driven techniques that I'll talk about next. And then we have the remaining backgrounds that are estimated from either a combination of data and simulation or just simulation. And these are processes that typically have at least 2 gauge bosons. And in this case, it's typically a pair of same sign W bosons. And B quarks, so things like TT bar in association with the W or Z, and then a whole panoply of rare processes that we've never seen before, except this guy. And okay, there's about a dozen of them there, see, and every student can have a different measurement to go do, and we can eventually find all of these. But okay, let's go in and just talk a bit about the backgrounds, starting with the fake leptons. And actually, since I'm on the fake leptons, I should add while I'm here that I did this work with a postdoc at San Diego and a student at Santa Barbara. And I want to mention the student at Santa Barbara because he was an undergraduate here at Texas A&M. So some of you know Nick Amin. So Nick is, just wanted to say he's been a fantastic grad student, and a lot of the work that's in these slides actually was done by Nick. He's done a really great job. So keep sending us good undergrad.
Yeah, they could.
But okay, back to the content of the talk. So fake leptons, we already mentioned they come from a variety of places: heavy flavor decays in flights, just misidentified hadrons, conversions of photons and jets. And so with all of this and the large cross section for TT bar, you might rightfully worry: is this going to be the biggest background to the search? It turns out that if sort of naively out of the box, it is a very large background, and we take several steps to try to suppress it using a combination of improvements to the lepton selection and then to the fake rate method that estimates it. The fake rate method we use to estimate it is really, you can think of it as an ABCD method. In one dimension, it's some sort of extrapolation and ID and isolation. And the other dimension, in this case, you need to think of it in terms of sample selection, 1 lepton and no met, which is QCD and range where we measure the fake rate, or signal region. But really this is extrapolating. Can we extrapolate from QCD to TT bar? That's the real question in the fake rate method. So first, how do we suppress the fake background? Well, we improve the lepton selection by optimizing it for events with a lot of jets. The way we did that was to use 3 handles for the isolation. So one handle is what's called, on the experiment it's called mini isolation. Basically what it means is this, that the cone size is a function of the PT of the electron. Since as things get boosted a lot, we would expect that the decay products become more collimated, and therefore we can get away with a smaller isolation cone. We also look at a larger isolation cone though for comparison. So in this case, by larger isolation cone, what we mean is we find the jet that contains that lepton candidate, and we compare the PT of the jet and the PT of the lepton. A real lepton, because of reconstruction details of CMS, will always give you a jet, the first order, and that jet will typically have all the momentum of the lepton. It'll just be one, peak L1 is what you'll see. But you can also get leptons from other sources where this very much might not be the case, like a semi-leptonic V decay. So we want to look at both and compare and see, does it look isolated in both ways? Now one concern with looking at a larger cone though is you have a lot of stuff in the event. You know, stuff can just randomly fall in by accident and you'll lose efficiency. And so to try to gain some of that efficiency back, we also look at a variation on PT rel. This is the relative PT of the lepton. It's this green guy. The relative PT of the lepton being the red, to the lepton subtracted jet. So we take the jet in black, we remove the lepton, which gives us the peak, and then we calculate the component of the lepton momentum perpendicular to that. Turns out that this is a useful handle for trying to identify accidental overlaps, where you have a lepton that was there and some jet kind of partially overlapped with some of the cone. And so by requiring that it's isolated and that it passes either the large cone isolation or the PT rel, it gives us a balance of rejecting fakes while maintaining as much signal efficiency as possible in an event with a lot of jet activity. Okay. With that selection, then we have to go and we have to measure the fake rate, which we do in a QCD enriched sample. And the way we obtain this is we go to collision data, we ask for events that have one and only one lepton. That lepton is well separated from a jet. There's no jet within nearby except for the jet that contains the lepton. And we ask for low MET and small transverse mass between the lepton candidate and the MET. These help to suppress contamination from W plus jets production that gets selected in here, as well as some Z plus jets production. And we measured it. So here you can see example of the fake rate for muons measured. It ranges, for the word interested, kind of 20 GeV and above, so fake rate's typically 5 to 10%. Of course, this fake rate had to be corrected for residual contamination from electroweak processes. So what we do is we invert the MET and MT cuts. We go look in the MT bulk where we think we have all W's and Z's. And we look at higher MET, which would enrich us in W's. And we normalize simulation to data. And we take that scale factor and apply it to simulation down at the low MET and low MT end to subtract off the amount of W and Z contamination that we expect in the region where we measured the fake rate. Now it turns out you may be noticing that the data looks kind of ugly. It doesn't look very W-like, and it just takes off. We're in the process of changing the approach for the future in that this peak used to be very clean if you go back to 2010. We now have 40 pile up instead of 5. The net result of that is that the MET distribution for QCD has gotten a much longer tail, and so we have lots of QCD now that's spilling in. And so we're replacing what is essentially simply a division of two numbers, but doing a fit to the components. We get templates from simulation now for what we expect QCD to look like, what we expect W's to look like, and we fit this to obtain a somewhat better estimate. But in the end, the net effect is it's a order couple percent effect on it, because it's a small effect on the fake rate, and fakes are only a small part of the background, so it's not a big effect, but pointed out because it is kind of glaringly obvious that the data just shoots up as we go to low MT. Okay, so with the fake rate in hand then, we need to try to estimate the background. It turns out that there's a lot of challenges in here that we spent a lot of time a few years ago trying to sort out, because the method only works well provided this fake rate that you measured in QCD events really can be applied to other samples, to TT bar events. And so you want to try to understand what differences are there between the samples, and can I parameterize those differences away so that I can really measure it in one sample and apply it in another. So the most obvious difference is lepton kinematics. The lepton PT spectrum will look completely different in TT bar events than it would in PCD events. And so we want to parameterize the fake rate as a function of both the lepton PT and the lepton eta, because it matters where in the detector the lepton goes, because there's different amounts of material that affect the isolation distribution. Then we also have to potentially worry about the PT and flavor of the parton that gave rise to the lepton candidate. The reason we have to worry about that is if you look down here, let's take muons for example, and let's look at just the narrow PT range, 20 to 25, and just in the barrel. We're just going to focus on centrally produced, and we're going to look at muons that come from bees. So we go to simulation, and we look at the, this is the PT spectrum of bee quarks that were the mother of the muon candidate. So these are bees that underwent semi-leptonic decays. We found the muon, and we're plotting for these muons what the PT of the parent is. We can do it for those that pass the loose selection. If you recall in the ABCD method, we had a loose selection and a tight selection. So we're going to compare the bee quark PT in those two regions, regions D and C. And in the bottom is the ratio of the red and black, which is effectively the fake rate. And what you see is that it has some structure for values of B quark PT near the muon momentum. And then it quickly asymptotes to its very small values. Now the reason for this is just kinematics. If you have a 22 GeV B quark and it gave you a 20 GeV muon, of course it's isolated. There's nothing else around to make it not isolated. You don't have a choice. So the fake rate's very high when the muon momentum and the B quark momentum are close to one another. And when they get far apart, well, now there's a lot of other stuff left from the bee that can follow the cone, and it's not isolated. And so the fake rate's very small. That's the reason for the behavior you observe here. Then we can also compare what the B quark PT looks like for loose muons, so these black guys, both for QCD events, which are in red, and TT bar events, which are in black. And you see that the PT spectrum of the B quarks looks very different. So we have a difference in what the B quarks look like between the two samples, and we know that the fake rate depends on the kinematics of those B quarks. So we need to try to parameterize this effect away somehow. Okay, and that leads us to improving the fake rate method. So how do we do that? Well, one thing we can do is that loose selection is not set in stone. We make up what it is. So we can construct a definition for region D such that the fake rates become about the same irregardless of the flavor of the parton that gave us the lepton. So it can be the same for muons from bees, muons from charm, and also from decays and flights. You can't do this perfectly, but you can do it well enough. Then once you've done that, you've gotten rid of one of the three parameters. So now you have three. Still like to reduce it more if you can. And one of the things you can do is you can try to combine information about the PT of the lepton and information about PT of the parent parton. And the way we do that is to define something called PT cone, which when the lepton passes our tight selection is just the PT of the lepton. And that's fine, because in those cases, the PT of the lepton and the PT of the jet are about the same. But when it's not isolated, then the PT of the lepton is actually a bad proxy for the PT of the parent parton. What we really want to do is multiply it by 1 plus rel iso. Rel iso here is what fraction of, what is the, let me just write this down. By rel iso, what I mean here is I have a lepton, and I open some cone about it. And rel iso is basically summing the energy of everything in that cone and dividing it by the PT of the lepton. And so if I include that in here, I'm basically saying I should treat both the lepton plus what's in the isolation cone as a proxy for the PT of the mother parton. And so then I'm going to write my fake rate, not in terms of what I said originally, but now in terms of PT cone and the eta of the lepton. Okay, that's all I need to parameterize it and reduce a lot of the dependence that we saw in the previous slide. We've done this. We perform closure tests in simulation, which means we take simulation, we ask, I want to have a muon that came from a V in a TT bar event that I think is a lepton, and then I'm going to try to predict it with my fake rate and compare the two. And the agreement is excellent. We used to have, say, things agreed at the 50% level. Most cases now they agree at the 20% level, 30% at worst. So it's been a significant improvement in our understanding of how do we model and estimate what is otherwise a very difficult instrumental background. And so with this, we think we have it decently under control. Okay, the other background, I'm only going to spend a few minutes on it because it's not very relevant for the analysis. It's a negligible background, but it's charge misidentification. Turns out it's negligible for muons. We basically always measure the charge of a muon right, but that's not true for electrons. We get the charge wrong actually not so infrequently. 10 to the minus 3, 10 to the minus 4 level. There's a lot of electrons being produced. But we can suppress that some by requiring that 3 different methods that exist to try to reconstruct the charge of the electron all give the same answer. So the first 2 are just 2 different algorithms to reconstruct the track from the silicon detector. One uses a Kalman filter. It assumes basically that the particle is a pion. The other, a Gaussian sum filter, basically it allows for a broader road to search on, or broader window to search in, because bremsstrahlung can cause the trajectory to deviate more than we would otherwise expect. And then the last is just a simple delta phi between the pixel hits at the very inner part of the detector and where the particle enters the calorimeter after it's traversed the magnetic field by a meter. So particle certain charge should always bend a certain way, and we can use the combination of these 3 to get about an additional order of magnitude suppression in the rate at which we mismeasure the charge of an electron. Okay, then where does the mismeasurement rate come from? Well, we take it from simulation, a combination of Z and TT bar Monte Carlo. We parameterize it in terms of the PT of the lepton and the eta, which are the 2 primary things that affect the rate. And then we cross-check it by going to data, looking at observed same sign events that are in the Z peak. So we want just 2 electrons of the same sign, which is invariant mass is consistent with the Z, and we compare them to what we would predict if we take the opposite sign Z sample and reweight each event by this transfer factor. And you see the comparison here. You want to compare the green and the black, and it's actually a very good agreement. There's a slight difference in mass shape, but not a lot, and we're not sensitive to that part anyway. And slight difference in the PT, but overall we agree to basically the ratio here is 1.02. Okay.
Well, what's from predicted at MC?
So we're also overlaying, if we were to take Monte Carlo dead reckoning for how many same sign pairs we expect, and we we just scale it to luminosity, what would it predict? And so that's the blue. We're comparing all 3 of these. This doesn't really matter. It's kind of there as a reference point to gauge how well the simulation's doing, but what really matters for us is how well do the black and green agree. And they agree very well. All right, so we covered all the data-driven estimates. Now let's talk a bit about the normalization. So modeling of addition jets. All right, so all the remaining estimates are based on simulation, at least for the shape, if not for the normalization. We're requiring at least, some regions we require up to 8 or more jets, which means that for a process like TT bar W, which would give a same sign pair plus 2 Bs plus 2 jets, we would have 4 jets. We need 4 additional jets. It's a lot of additional jets to ask your simulation to model correctly. And so we want to check how well does the simulation model NJ. So to do that, we select opposite sign TT bar events. We require exactly 2 B tags. We count the number of additional jets in the event, and we compare it between data and simulation. Here it's for MagGraph and NLO. You can see a comparison. It's not bad, but there is some mismodeling. Out to 4 jets, the difference here is almost 20%. And so we want to correct for this. So we will actually apply this as a correction factor to our simulation. For every event that passes our selection, we'll count the number of jets that are not from the lowest order matrix element, and we'll rescale it by an appropriate amount. taking half the difference as an uncertainty. Okay. You might also ask, well, you're asking for up to 4 B-jets. Well, you know, TTW has 2 B-jets. So where are the other B-jets coming from? So what we did is we took this TTW process and we looked at generator level and we asked, where do the events come from that have 2 B tags? And it turns out that 80% of them are the 2 Bs, and half of the others are 1 B and 1 charm. The 3 B tags are generally always, here we go, 2 Bs and 1 charm. The reason why charm keeps popping up is because we've asked that this W decays leptonically and this W decays leptonically, which means this W is decaying hadronically, and half of all your hadronic W decays contain a charm. So there's a lot of charm flying around in these events. And the mistag rate for charm is more than an order of magnitude larger than the mistag rate for light flavor. So it's easy to get extra fake B tags. Turns out when we get 4 jets, by 4 B tags, it's almost all due to TTW with 4 real Bs, which must mean we had some gluon that split the BB bar. And so the other thing we need to check is how well do we model additional BB bar production. So we can try to check it. There have been measurements done of TT bar, TTBB over TTJJ. It was about 1 sigma above theory when it was mentioned. You can see the results for the number of B tags here. And so we apply this correction to simulation. We basically go into simulation, we say, does this event contain a gluon to BB bar in addition to, say, a TTW event? And when it does, we scale it up by this amount of this insert. Now, more recent measurements that will come out soon basically show that this agrees much better, and so the correction in the future is going to be about 1. All right, so now that we think we can correct the simulation like we need, let's actually go look at TTW and TTZ in the control regions. Our TTW control region is a same sign lepton pair, no more than 5 jets and exactly 2 Bs. This is orthogonal to the rest of the signal regions. We look for 4 top in. We don't expect much 4 top here. And CRZ, which is for TTZ, requires 3 leptons, with 2 of them making an opposite sign, same flavor pair consistent with the Z. And we were asked for at least 2 B tags. The results shown here are pre-fit, which I'll go into a little more detail in a couple slides. The post-fit quantities you need basically are you scale the data to scale TTW by 1.2, scale TTZ by 1.3. As a cross-check, we compared these against the actual measurements of these processes, which are done with the same data set, but are partially overlapping and not quite the same selection, so trying to use their numbers complicates the statistical interpretation, so we do it on our own. But you can see their best fit measurements here compared to what the theory would be, so they're high by about the same amount as we are, about 20 to 30% higher for both processes. Okay. So that's TTW and TTZ. Those are the 2 dominant backgrounds of this type. The third one that's important is TTH. It mainly enters the analysis when the Higgs goes to WW, so it's a TTWW final state. Sorry, that should be 500 femtobarns for TT Higgs times 20% branching ratio for Higgs to WW. So it's about a 100 femtobarn process compared to 10 femtobarns as we talked about at the end of the signal. So it is quite a bit larger, but it does have 2 fewer B-jets. This process is much less well understood than TTW and TTZ, so what we chose to do at the time was just scale it to luminosity, and based on the Atlas and CMS measurements that were available at the time, we chose to assign a 50% uncertainty to it. Even though the theory uncertainty in the cross-section is about 10%, the measurements seem to indicate that the more conservative uncertainty would be warranted given these measurements aren't sensitive enough yet to really clarify for us where things are at. Now you may notice that this 1.5 doesn't look at all like the 1.2 in the plot I put at the bottom, and that's because since this analysis was approved, an updated combination has come out where CMS includes multileptons and taus. And you can see the taus tend to be, there's one tau that's way low. And then here's another tau that tends to be low, and this guy's kind of right at the average. But the net effect of these is that it pulls the entire average down from 1.5 to the best fit being about 1.2. And so this also is likely, as we get better and better measurements of this is likely going to end up becoming closer to 1, and we'll probably take a smaller theory uncertainty to reflect the state of the current measurements. Okay, other processes. We have all these little processes left that I didn't mention. There's a whole smorgasbord of TTVV TT processes. We generate these all at leading order with MAGRaph, no additional partons, and then scale them to NLO cross-sections. They come from this handbook. The biggest and the most important is TTWW. It's about half of the remaining background. We did a fair amount of study on this because we had some concern at the time, are we double counting events in TTWW and TT Higgs to WW? It turns out we're not. As you know, when the Higgs decays, generally one of the W's is always off shell, and this is generated requiring the W's to be on shell, so there's effectively no overlap when this happens. Okay, last one, X plus gamma in rares. These are estimated from simulation. We could have done something more for the conversions other analyses have, and they've shown that it's modeled very well, so we just took the simulation because what these guys did is they defined a tri-lepton region. So they asked for 3 leptons, an opposite sign, same flavor pair whose mass was about 75 GeV, so below the Z mass, below MET, to enrich it in Z events, and to suppress WZ. And then they reconstructed the 3 lepton momentum, which you would expect to be consistent with the Z, and it is. All right, those are all the backgrounds. Throw it all in the container, turn the crank, perform a fit to this with all the signal regions, all the control regions simultaneously fit them. I list here the uncertainties and all the things. Well, it's worth noting this analysis is completely statistics limited. The difference in the total uncertainty on the measurement, including systematics, or setting them to 0, is 10%. So it's a small effect overall, which is good. We're not yet at the regime where we really need to push out every last little bit of understanding. So here's the post-fit results. We saw earlier the post-fit scalings of TTW and TTZ, 1.2 and 1.3. TTH moves by just about 10%, so it seems consistent with the standard model. Notice that these uncertainties, if you compare them to the previous slide, so we took a normalization uncertainty on TTW and TTZ of 40% and TT Higgs of 50%. These get shrunk somewhat. They're getting shrunk basically by the available statistics in those CRW and CRZ control regions, so they get down to about 30% uncertainties instead of 40. The TTH doesn't get constrained at all because there's not enough events to really do anything there. Before we move on, you can look with Sally, no stunning departures from the standard model. So likely no heavy Higgs is just waiting around the corner, but maybe tomorrow. Here's the post-fit kinematics, and leptons and jets and V being the 3 major ones we classify events by, and you see things look reasonable. All right, so the results, what are the numbers that come out when this is all said and done? Well, there's a bunch of questions you can ask. One is, what is the upper limit? So this is what we've been doing a lot up to now, and that was the first plot I showed you, right? What is the upper limit if standard model 4-top didn't exist? It's about 20. We observe 40. Well, we observe 40 because it's actually there. And 2 sigma difference is about 20 femtobarns. The signal significance we can ask with respect to the background only hypothesis. We expect 1 sigma, we observe 1.6. Get a small excess, but not really much of one considering the large uncertainties, as you'll see, because we can then turn that into a cross-section measurement. We expect, if we assume a theory input of 9.2, that we would get 9.2 plus 11 minus 8.6, so measure it with 100% uncertainty, and we observe 17 plus 14 minus 11. So the 2 numbers agree within very, very large uncertainties, but it's nice to sort of be moving in the direction of a measurement as opposed to only setting limits. Just to remind you, this was one number, this was the NLO number from the MAGRaph authors. If I take the leading order number and I apply it the K factor that the 14 GeV could forget, which isn't so unreasonable, factor about 1.2, which starts to C. This is 12.2. These are all consistent for now. So no ability yet to kind of differentiate them. We can use those same results to set constraints on heavy Higgs. So we did that. And for tan beta equals 1, we just did it for one value of tan beta now because our sensitivity is limited. We are just starting to be able to probe these scalars around twice the top mass, just where this gets interesting. So we exclude scalars below 360, just getting a little bit of sensitivity. Pseudoscalars have a somewhat larger cross-section, so we're a bit more performant. We exclude them out to about 430. This is really complementary to the other efforts that we saw on this, because it's, we saw the other efforts were probing masses around 500. We're able to probe the lower mass region that's interesting, right near twice the top mass. And also we saw that there was a dependence on tan beta because there was a dependence on the width for fitting the resonance. We basically are insensitive to the width because we're just counting multiplicities. So we expect that as we increase data set ultimately by a factor 3 this run, that we can turn these into some 2D exclusion in the tan beta scalar mass plane, and that we'll be able to, by the end of run 2, actually rule out a significant chunk of the low mass interesting region of this plane. What else can we do? Well, I mentioned earlier that we depend on the top Yukawa, which means we can turn this around and we can say, having measured at the 1 sigma level this cross-section, can we turn it into a constraint on the top Yukawa? Now when we set out to do this, we thought that this was great, this was super easy to do because there would be no model dependence in this. Just taking the 4 top, I mean, all you're assuming is the form of this, but there's no dependence on anything else in Higgs world, whereas current constraints on the top Yukawa typically come from some complicated fit that involves lots of measurements and hundreds of thousands of nuisance parameters, and it's hard to understand. It'd be nice to get at it so easily as this. It's a little more complicated because of the non-negligible background from TT Higgs, which also scales as YT. It scales like YT squared. And that's what results in this observed cross-section limit being kind of curved like this as opposed to just a straight line. But okay, you could we made this 2D plot. This is the prediction for the cross-section as a function of YT based on these numbers. This is the upper limit, and this is the best fit cross-section value. And so based on these, I mean, you can choose to pick in different places where you would want to read out the constraint, but it doesn't matter so much. It's around 2. We can constrain the top Yukawa to be less than twice the standard model value, just based off 2.2 it is or something, just based off of this measurement. It's not competitive yet with the best results from the fits, but it's a heck of a lot easier to understand, which is kind of nice as a cross-check, and it will become, it will improve much more rapidly than the other one that we're getting this up and going. Okay, so time is winding down, so just a couple of slides, I think, to sort of show where this could go in the next year or two. So with 2016 plus 2017, which is already on tape, we just need to analyze it, which should be about 75% of barns. We're aiming for a result this summer. It will have some small improvements to the event selection, and the larger data set will let us be a little more aggressive. So we're going to end up performing what amounts to a full shape analysis in NJ and NB for the cut-based analysis. And with that, we expect about 2 sigma sensitivity. And we also are now training a PDT to look at this as well. And we want to have both of these, certainly the cut-based at minimum as a cross-check. This gives us, you know, what you would expect, about 20–25% more sensitivity, so we get about 2.5 sigma. If we do the same thing for the full run 2 data set, which we would aim to have a result of spring, summer 2019, and for which there may be some more substantial improvements to lower level quantities since we have more time. The cut-based shape analysis gives us 2.5 sigma, and the BDT analysis 3 sigma. So we're going to be approaching right at observation sensitivity by the end of run 2 with just this analysis, and of course we'll combine with the 1 lepton opposite sign, which will give us some further improvement. So we expect more than 3 sigma significance, certainly with the full combination of channels. Other things, I expect we're going to probe a lot of the region of 350 to 500 for tan beta, say below 2. I don't know how much yet. We haven't run the numbers, but there's going to be an interesting region that's excluded. There'll still be a little bit that remains. We also think we can have improved much tighter constraints on the top Yukawa. Yeah, last one. So it turns out there's other cool things you can do with 4 tops related to the Higgs that we didn't do the first time around, but we're starting to work out. My first time trying to explain it, so it looks complicated. I'll probably make a mess of it, but let's give it a try. These guys, Chow and others, proposed that we can combine a 4-top measurement and a TT Higgs measurement to constrain the total Higgs width. Now, some of you may be familiar with the current constraints on the Higgs width, which comes from on-shell and off-shell ZZ production. It's the same idea here. So on shell, produce a Higgs on shell, and what do we can write this as some signal strength times the standard model cross-section, how this is often recorded. But we can also write this as the standard model cross-section times KT squared from the production vertex, times KX squared for the decay, whatever it is that the Higgs is decaying to, and then a ratio of widths of the actual Higgs width to the standard model Higgs width. We can rewrite this, combine them to write it in this form here, and we have a current public measurement from CMS of mu-TTH, which is multi-leptons plus tau. This is usually this number, observed expected. We also know that the off-shell part goes like KT to the fourth. That's what we saw earlier. So if we make an assumption, two assumptions right now, that KT on-shell and KT off-shell are actually the same value, and that Kx, whatever the x is 1, that it takes the standard model value. You don't have to make that assumption of 1, but it makes it easier for doing it, otherwise you have to do some fits. Then you can rearrange all of this to show that RH, which is the ratio of gamma H over gamma H standard model, that's equal to KT squared divided by the measured mu. Well, KT squared we got an upper limit on from the 4 top measurement. So I'll just use that number, 2.1. And the mu, I'm using the expected one because I want to get what is the expected constraint on the width. Okay, here I do it at 1 sigma, right? 1 minus 0.38. I do that, I get 7. So this analysis right now, combined with the TTH, would be expected to constrain the width of the standard model Higgs to 7 times the standard model value. If I do the 2 sigma, which is maybe you could argue the better one to do, then I constrain it to about 18 times the width. About 75 MeV is the constraint you can get from the back of the envelope, what I did on the plane with this. And also, if we did the projections right by hand in the plane, we expect to factor a few improvements. Something like the total width of the Higgs can be constrained to 5 to 7 times the standard model value by the end of row 2 with just this measurement. It's constrained about will be constrained about a factor or 2 better than that from the ZZ, but this already is becoming interesting enough to include in some total determination of the Higgs width. And this is kind of a very neat thing, again, that falls out in a relatively simple way from just this single measurement. So okay, I think 4 tops are an exciting window to the standard model and beyond. We're closing in on the first observation of 4 top production. We provide an independent complementary constraint on the top Yukawa coupling. We probe interesting scenarios with additional Higgs particles, in particular 2 HDMs in the low tan beta alignment limit. And we can combine with other measurements, TT Higgs, which I won't have time to get into, we're getting involved in TT Higgs Higgs to gamma gamma, and so that combined with the 4 top will give us the best limit on things like the Higgs width that we can get from this channel in the next year or 2. And so I'd leave you with sort of, this is a view from the top. I mean, remember, we started here 20 years ago, 25 almost now, with the discovery of the top quark. And we've come a long way since then. All of this now is sort of standard bread and butter for the collider experiments, and we're now getting into this whole new region of exotic multi-particle production. So where will we go tomorrow? Well, I think we all still hope that something like this is the future to aspire to. And since I was born a Cubs fan, I guess I only had to wait 36 years for it to happen. You know, if they can do it, why can't we?
So, okay, for question. So I have a question.
Mm-hmm.
So with the width measurement from the off-shells, etc., how do you compare?
They're better, right now they're better by a factor of 5.
Okay, so would it make sense at some point to combine?
I think it will at some point. It doesn't, and also, like I said, I did, just to be clear so that no one, these numbers shouldn't be repeated. I really did this on the plane, like on the napkin, so it's probably about right, but not worth quoting. We are gonna start working with, we have to work with the Higgs group and go through this whole process in order to actually put out a number. But yeah, I think we want to, and I think by the end of it, this will improve more quickly relative to the other one because it's where it's starting at. I think by the end of run 2, we could be within a factor of 2 of them, in which case it would really make sense to do a combination. Yeah.
So, it seems that you will improve if you're able to resolve jets in the overlap, right?
Right.
There are some plans to try to solve for this, because you can apply some, I don't know, jet substructure analysis and
Right.
try to recover these jets.
So we've looked into a variety of substructure approaches. I mean, one of the first things we were strongly, we had some debate putting out this paper the first time is why don't you look at hadronic top tags? It turns out that hadronic top tagging doesn't help us here because of this point we just talked about, the overlaps and the lost jets. It basically means we never get all the jets from a hadronic top. We then said, well, okay, we're not getting the hadronic top, but what if we just get other jets overlapping? And so we tried to do things like look at jet mass over PT for the highest jet that had the jet with the highest value of jet mass over PT, or look at putting substructure outputs from the the various discriminators in our VDTs. None of it really. 1 or 2% improvements, nothing more than that we've seen.
I have a small comment on the fake rates. I've become an old person. So, 12, 13 years ago at CDF, people have been working on TAUs, people have been spending a lot of time trying to improve modeling the fakes. And at some point we had a major breakthrough. Things started looking wonderful. Then we realized that there are big dangers in trying to come up with variables in modeling the fake rate, parameterizing fake rate, if these variables have any connection or correlation with any of your important IT variables. It's incredibly dangerous. If you think, like in the most extreme scenario, imagine you take your IT variables and parameterize your fake rate against them. It becomes 1 within the cut, 0 outside. Yeah. If you do it without realizing that you have done it, any sample you take and you run your fake rate estimation and compare with the actual location of IT cuts, you get the exact same results. You have wonderful agreement between the prediction based on your fake rate prediction and actual location of IT cuts, which is the way to test these things adding up, right? When you go and apply the same technique to a real data set, you can hide any signal that could be there just because your prediction based on fake rates will exactly match what you get by applying IT cuts. And I saw that you have been you've been redefining PT, you've been, this is...
Redefining PT as
how do you know that?
The PT is not redefined for what's used for anything except looking up the right value of the fake rate.
Right, but you added it into the, you took the isolation stuff, put it in PT.
That's right.
Yeah?
Yeah.
And that's actually path of trying to incorporate it's very correlated with UID variables.
No, I don't agree. It's not, especially for muons. There's zero correlation in muon, basically. One has to do with the fit of a track and whether or not there's matches.
We don't need to agree now. You should think about is this statistically even probable to have an agreement like this between the prediction and?
Sure. I mean, it's.
Can you check the chi-square of those predictions you have?
Yeah, sure we can.
Because that's actually the simple.
Yeah.
The chi-square ends up not being too good.
Yeah, sure, right. If the chi-square is close to 0, then we have a problem. But I mean, I can certainly pick other ones that have less good agreement than this. This is just I chose this one.
No, look, I mean, what I described is a completely extreme scenario.
Yeah, sure. But your point's taken, and it is tricky.
But whenever you go in the past, when your variables in which you use in your calculation of the fake rates are correlated with your actual IT variables, they're correlated with the strongest IT variables.
Well,
if
no,
you're thinking of the way
no.
you calculate uncertainties on the background after all, implies that these are uncorrelated, right?
Well, I think I'm not quite getting what you're saying. So say I have I normally have a B that gives me a lepton. The only handle I have to discriminate this B to first order is isolation, because it's a real lepton. Impact parameter a little bit, but it doesn't help that much. So isolation is the only thing I have essentially is my ID, if you want to call it. And isolation is the only thing I have to extrapolate. But it's not at all, there's no reason why this agreement has to work out this well. Before we did this redefinition, the agreement was terrible. So I'm not sure I understand.
I mean, we can take this.
Let's take it
offline, but I
offline,
think you
because-
should, what I would do, I would carefully check the chi-squares.
Sure,
on
we can do that.
Various tests when you compare the prediction of the fake rate with actual. So whenever you test your technique, right, you run actual ID cuts on the background sample.
Always,
And compare it with the prediction of fake rates.
always, that's,
And so by looking at various samples, I would check what is the chi-square too good or not. Because if it's too good, this will indicate that you incorporated your ID in the fake rates, and that would be very dangerous.
yeah, let's take it offline now. Other questions?
Okay. Then we failed